Warm weather arrived a little bit early this year, and as part of some preemptive maintenance, it's time to learn about brushless fan control. Mechanically, the 16-inch SPAL polar fan should bolt right up to the stock shroud. However, the control system is definitely not plug-and-play. In fact, documentation beyond basic specs, airflow curves and such was a bit difficult to track down. I had to do quite a bit of hunting, but I think I pieced something together. The fan uses a Yazaki connector with 4 terminals. Here's a cross-section of the connector: red positive, black negative, yellow signal, and white signal. If the white is listed PWM, the yellow listed A, makes me think analog control, and that is backed up by this other document. According to this chart, there's 8 different control strategies that can be used with this drive. Connect analog to battery positive, PWM to negative, and then switch it on the negative side. Current rating of the switch, of course, has to handle the full running current to the drive, but because it is soft start, it will not have the massive inrush spike of a standard brush motor. Same setup, except switching the positive side instead of the negative side. On-off with enable low. Drive has constant power, analog line is constant to positive, except the PWM line is switched to ground to enable the fan. This allows a low current switch, or ECU, output to command the fan to run without having to pass the full drive current. Now here's where things start to get interesting with speed control. Can have switched power with the PWM tied to the negative side and an analog signal in on the A wire. After initialization, the drive goes to the speed requested by the analog input. Same variant, except switching the positive side, and a variant where the drive is constantly connected to battery power, but the PWM line is pulled to ground to enable, coupled with an analog input for the speed control. Next, have digital control with PWM. Analog connection is left unused and floating, whereas an active low PWM source controls the speed of the fan and also the wake-up. It can be any active low open collector, transistor, MOSFET, even a switch if you can get one to go fast enough. Priority is with the PWM signal, so if it has both, it only pays attention to the PWM. To make my life easier, I did pick up this pigtail kit along with the fan. This should let me pretty simply plug in like that, and then I can access these wires however I see fit. Gonna start off pretty simple. This is mode 1 or mode 2. White PWM enable is connected to battery negative. Yellow analog input connected to battery positive. This should result in a soft start ramp up to full speed. For sanity's sake, I have this pointed so it's going to try to suck air through the workbench and throw it upwards. I don't exactly want this thing achieving liftoff on an initial power-up test. While I don't have a bench supply big enough to fulfill the 40 plus amps this fan is going to ask at full load, I do have this retired battery. I don't trust it as much for starting, but it should have plenty of grunt to get this thing to spool up. Oh! A little bit of a inrush snap there. Okay. Oh, we got movement. That's spooling up. Wow. Okay, yeah, that works. Here's the setup in mode 3, constant power to drive, but if I connect the white wire to negative, that should do the same thing, where it will wake up and begin to spool up to full power. Got a nice gradual ramp up, and a little bit of a faster ramp down once the signal's removed. Moving on to testing the analog control. I have the yellow analog wire hooked to the wiper of this 1K potentiometer, which is connected between battery positive and battery negative. PWM enable line is tied to battery negative, so the drive should be awake right now. And if I turn this up, we should see something on the fan. I don't know how much of a dead zone there's going to be, or what else it's going to do, but now is time to find out. Slowly ramp the voltage up and see what happens. Still no sign of life. Oh, never mind. Whoa, 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 what? Is it turning backwards? Hold on, let's try that again. It's like 1.5 volts. Yeah, that's doing something weird. And yes, that is definitely going backwards. This is a puller fan, so it should be pulling up through the workbench and throwing air out this way, rotating counterclockwise from this perspective, but just now it was rotating clockwise. I think the minimum listed speed for this is 850 RPM, and that sounded a little bit faster than that. Try one more time and just see what it does. Provide some downward pressure in case we attempt to achieve liftoff. Yeah, that sounded like full speed, and it was certainly getting floaty. It felt like it wanted to start picking itself up off the bench. But why? Don't really see anything in the documentation here about how the analog control is done. Is it inverted? That doesn't explain why it's going backwards. This blade is unidirectional. It's a polar optimized blade. It will flow air, but it's not going to flow very well going backwards. So maybe there's multiple modes. Add a little bit of ballast so the fan can't fly away. Going to ramp it up through that 1.5 volt regime and just see what it does. Multi-turn pot would make this a little bit easier. It's fairly sensitive. Just try 3. Oh, 3. Now that's going forwards. Aha, there's multiple control modes on this thing. It is now going forwards at a very low speed. It is not ramping up any further. I need to start writing this down. What happens when... Oh. Okay, so that was a reverse point. Like 2.5. Yep. Okay, this is getting weird, because I had it at 3 volts before, but it was going forward at low speed, but once it was going reverse, it seemed like it was locked into reverse, even though I brought the voltage back up. Okay, it's in reverse mode now. Going to pull it down slowly to see when it shuts off. Okay, so a little bit under 1 volt, it appears to shut off. Looks like around 3 volts, it begins low-speed forward operation. Alright, it's starting to make sense. There's definitely hysteresis between the different modes. Bringing it up off 3 volts, no audible change in speed. Oh, above 4 volts, the speed appears to increase. Same speed from 3 to 4 volts, but above 4 it speeds up. Now it's making sense. After that on-camera and some more off-camera testing, this is my rough chart of how it responds to the analog input voltage. 0 volts is off. If the voltage rises above 1.5, it starts running full speed reverse. If the voltage goes back below 1 volt, it stops the reverse and goes back to off. If the voltage goes above 3 volts, it will begin forward minimum speed operation. But if it goes below 2.5, it'll stop going forward and start going full speed reverse. Between 3 volts and 4 volts, it seems to run at minimum speed. Then between 4 volts and 10 volts, it ramps up to full speed. Above 10 volts, the speed does not increase. Deadbands I understand. Still not quite sure why it would have that reverse mode regime, but maybe there's some application of this fan or this drive that would require full speed reverse. I know I've seen refrigeration units with a different fan design that could blow reverse to help clear dust off a condenser coil, for example. And now for something silly, because I've really got to know. Can this fan make enough thrust to lift itself? The answer is yes. For this fan model, minimum speed is listed as 850 RPM and the maximum as 3150 RPM, so that gives the minimum speed as about 27% of full. Since that's in the 3 to 4 volt mark, gonna call that 4 volts for 27%, assuming a linear ramp, which I have no reason to suspect it wouldn't be linear. 6 volts should give 50% speed roughly, 8 volts 75%, and 10 volts should give 100% speed. Moving on, there is 38.7K between the analog wire and the battery negative cable. Based on what I found so far, it's entirely feasible to use a voltage divider or a potentiometer to control the analog voltage in, and therefore the fan speed. With the caveat that there's that reverse operation regime, so might want another resistor on the negative side of the potentiometer to raise the minimum voltage that it outputs when turned all the way down to something that will result in minimum fan speed. By having multiple voltage dividers and switching 12 volts to either of them can have various stages of fan speed. Use diodes to prevent backfeeding from one to the other. 2 are shown for simplicity, but there could be 3, 4, or however many you feel like building. The high-speed one could even skip the resistors and directly connect the 12 volts to the analog input, since anything above 10 volts or so should result in full speed. Which brings me over here to how I would control this fan from the Volvo stock ECU that uses a 2-stage low-side switched relay pack to control the stock brushed fan. I could not use the stock Volvo fan relay as that does something clever to provide a form of soft start for the brush motor. It uses the back EMF of the motor to activate the relay coil for the high-speed contact. In effect, the fan must spool up to some appreciable fraction of low speed before high speed can engage. In this case, I would use some diodes, the resistors dividers, and 2 relays in order to command the SPAL fan. 12 volt power goes into one side of each of the relay coils, as well as to the relay contacts. When the Volvo's ECU pulls the other side of the coil low, we'll use low speed for example, it will turn on the relay, providing voltage to the voltage divider, sending power through the diode to the analog input of the fan. In this case would be half power command. At the same time, it would sync current through this diode, pulling the PWM enable line low, waking up the fan from its sleep mode. High speed would do the same thing through its diode, its relay, and either another voltage divider for say 80% speed, or skipping R3, removing R4, and directly connecting 12 volts to the analog input for maximum fan. Toss together a prototype based on the diagram I just showed. 2 relays, 4 diodes, 2 resistors for voltage divider for half speed, direct connection for full speed. I do have an inline fuse now, just so I don't let the smoke out of my new breadboard. If I connect the other side of this relay coil to ground, there's a click, and got exactly 6 volts on the output. Go over to this other relay, click. Now I have battery voltage. Controller prototype and the fan hooked to power now. Interesting, there's a slight positive voltage coming from the fan's analog input wire. As expected, nothing happens because neither of the relays are on, nothing is pulled to ground, so the fan shouldn't do anything. If I connect the low speed, the fan starts to spool up. Little bit of voltage sag, it's not a perfect system, and the battery does not have a charger on it right now. But there's approximately half speed. If I connect the other relay coil to ground, we should get a ramp up to high speed. Yep. Similarly, if I go direct to high speed, should get the ramp up to full. Yep, that does the trick. Taking a quick look at the quiescent current of the fan, have it routed through the 10 amp range on the meter here. Nothing measurable on the 10 amp scale. See if anything shows up on the milliamp range. Not at 200 milliamps. 0.005 milliamps. Looks like it's going to draw in the low double-digit microamps when the fan is idle. Set back on the 200 milliamp scale just to be safe. Going to ground the PWM input to wake up the electronics. Look at that, 32 milliamps. Unhook it. After a couple seconds, it goes back to sleep. So from the looks of things, I could fire up the soldering iron, make this prototype into a permanent solution, attach it in place to the stock relay, mount the fan to the shroud, and call it done. Brushless fan with 2-speed control. However, that's leaving a lot of features on the table that I really wanted to take advantage of. For that, I'm going to need something a little bit fancier than a couple relays and some diodes. Moving on to the next phase of the experiment, PWM control of the fan. Got an Arduino Mega here, way overkill for this, but it's what I have for a test platform. Got a potentiometer rigged up on my breadboard here to use as an input to the Mega, and then I have a little NPN general purpose transistor to provide the PWM drive for the fan. Convinced my very old laptop to fire up, got a serial monitor going so I can keep an eye on what the Arduino is doing. I'm expecting a similar behavior table as with the analog control, with a few extras. Namely, as seen before, when this PWM input to the fan is allowed to float open circuit, it has an internal pull-up, so that will go to 12 volts. But I've already tested connecting it directly to battery negative, and the fan ignores that. It must see an actual PWM frequency in order to wake up and start responding. As a consequence of that, the PWM duty cycle presented here is inverted. So with the potentiometer all the way to the left, the Arduino is outputting a 0% duty cycle, but the fan is seeing that as 100% duty cycle. Going to be interesting to see how it responds to various duty cycles as I ramp this up. Okay, there's 10% duty cycle on the Arduino, which is 90% on the fan. That sounds like full speed. Whoa! And yes, as I increase the duty cycle on the Arduino, it effectively slows the fan down. Here that's 50% duty cycle. There's 40. There's about 30. So that feels like essentially low speed. Okay, lower the duty cycle to 19%. It's not slowed down anymore. Looking like 25% or so is the floor for minimum speed. Based on the analog curve, I'm expecting some sort of goofy reverse operation to begin any moment now. Yep, it just came to a stop and is now reversing, and that is at 15%. 7%, the reverse stopped. All the way to 0, still nothing. Bringing it back up to see where the reverse mode begins. Okay, so there's about 10%. This thing is so strong, even when it doesn't have any room to breathe, it makes so much turbulence it's throwing stuff off my workbench here. Reverse turned on at about 10% duty cycle. Yep, at 10% reverse is on. Now I'm starting to get a hang of this. Went ahead and mapped out the PWM behavior that I was able to observe. At 0% PWM, the fan is stopped. If it rises to 10%, the fan goes full reverse. If it falls below 7% while it's in reverse, it will go back to off. If the percentage rises to 18, it will begin minimum speed forward. Falling below 15% while going forward will initiate the full reverse. Above 25%, there appears to be a linear ramp up to full speed, which is reached at around 90% duty cycle. At 98% duty cycle, the fan stops, and it maintains its behavior up to 100% duty cycle. If the duty cycle falls below 95%, the fan resumes full speed. A little bit more complex than the analog one, but understandable, and it's nice to see this hysteresis so it doesn't oscillate between one mode or the other if the signal is borderline. To recap, this fan has pretty versatile control modes ranging from simply switching the power on and off to advanced PWM. The analog control mode was especially interesting to see because that would allow an older ECU to control this fan easily, just with a few resistors, diodes, and maybe one relay involved. The same technique could also be used without an ECU at all, using 2 temperature switches with different ranges. Boom, 2-speed fan control, advantage of the brush fan soft start, and higher efficiency. As for installing the fan on the wagon, that's a whole other can of worms and a whole other video. While I could do the 2-speed analog control like I showed earlier, I'm going to be making a PWM controller here. I already have temperature sensors I put in for the transmission and the oil temp, and I can do a few tricks to pull the engine coolant temperature from the stock sensor, and I might be able to get a high pressure signal from the AC as well. If I can combine all those, I can have variable speed fan, taking all of those temperatures into account. For that, you're going to have to stay tuned. Meanwhile, here's some options that YouTube thinks you'll like. Thanks for watching.